Happy learning! Today we're going to talk about counting, in particular permutations and combinations. Okay, so let's get started today by talking about the fundamental counting principle. This is going to be the math that's going to be happening behind the scenes when we do all the problems today. So this is the fundamental counting principle. And what does this rule say? It says if there are n of a, let's go lowercase, ways in which event A can occur, and if there are n of b ways in which a second event B can occur after the first event then the two events can occur in n of a times n of b ways. N of a here and n of b here are just numbers. Okay, and so if we want both events to happen, the number of ways to do that is you multiply the number of ways each of the events could happen. Okay, so let's take a look at an example. Suppose a restaurant, oh, and I should say that this counting principle extends if there were more events than just two. Okay, so if there was a third event, it would be n of a times n of b times n of c, right? You could see how this would extend. So suppose a restaurant has 3 appetizers, 8 entrees, and 6 desserts. Okay, so this restaurant has 3 different appetizers, 8 different entrees, 6 different desserts, and you want to select one of each to make a meal. The question is, how many different meals? All right, and we're going to say a meal has to have an appetizer, an entree, and a dessert. And so this will follow immediately from the fundamental counting principle. There are 3 ways to pick an appetizer, 8 ways to pick an entree, 6 ways to pick a dessert. So the total is 3 times 8 times 6, which is 144. All right, it's as simple as that. You multiply the options. Okay, let's take a look at another example. Suppose a person planning a banquet cannot decide how to seat the 6 honored guests. Okay, they're going to be seated in a row. So there's going to be 6 chairs. They have to decide how many or how to seat these 6 guests. in how many arrangements can they be seated? Okay, so let's give a quick little sketch of what's happening here. We have these 6 seats. And we need to decide who gets in the first seat and then who's in the next seat, third seat, fourth seat, fifth seat, and sixth seat. It's not like they're ranked. They're just like, this is just the order that they're going to be seated at this banquet. Okay, and so how we could do this is we could say, all right, who sits in the first seat? There's 6 options. So there's 6 options for who sits in the first seat. Once that person is decided, they're no longer eligible to sit in any of the other seats. Right? Once you get a seat, you don't get a second seat. You only need 1 seat. So somebody is seated in this first seat. How many options are remaining for the second seat? There's 5. Okay, now 2 people are seated. There's only 4 people remaining. And then 3, and then 2, and then 1. All right, so the total number is the product of these 6 numbers. Which is 720. This product, 6 times 5 times 4 times 3 times 2 times 1, has a special name. This is what we're going to call 6 factorial. Okay, this exclamation point means factorial, and that is 6 times 5 times 4 times 3 times 2 times 1. So n factorial is given by n factorial equals n times n minus 1 times n minus 2 all the way down to times 2 times 1. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 1 factorial is just 1. 2 factorial is 2 times 1. You might be wondering, what is 0 factorial? 0 factorial is going to be defined to be 1. It'll just make our lives a little bit easier when we're writing out our formulas. Okay? And so the answer here was 6 factorial. So let's take a look at another example. In this last example, the number of seats was equal to the number of honored guests. Now let's say there are 8 honored guests. But only 6 seats. How many arrangements can be made? All right, so try this on your own. Go with the same strategy. Draw out the chairs, draw out the seats, and say how many are available for the first spot. Once they're seated, how many are available for the next spot, and so forth. Right? These counting problems are really easy once you see the answer. But you're not going to learn anything if you just watch the answer. All right? So try it on your own. Struggle with it a little bit. Welcome back from the struggle. I hope you were able to find a solution. If not, that's okay. So let's draw out our seats again. So 1, 2, 3, 4, 5, and 6. There are 8 honored guests, and we have 6 seats. How many options are there for that first seat? Well, there's 8 of them. Okay? Now, one of the honored guests already has their seat. They don't need another seat. So there's 7 honored guests remaining. So there's 7 here. And then you can see the pattern, 6 times 5 times 4 times 3. Okay, so our solution is 8 times 7 times 6 times 5 times 4 times 3. This value is 20,160. Okay, and so this we're going to denote as 8p6. Okay, this is going to be what we call a permutation of 8 objects where we pick 6 of them. So let me define this so we have it in our notes. The number of possible ordered arrangements of R objects chosen from a set of N objects is called the number of permutations of N chosen R at a time. Okay, we write so this is the number of permutations. We write NPR. Okay, just like the public radio in the United States. NPR. We're taking an ordered arrangement of N objects and we're selecting R of them. And the formula for this is N factorial over N minus R factorial. Okay, so let's see if we believe that this value, 8 times 7 times 6 times 5 times 4 times 3, is really 8p6. Okay, so 8p6 is equal to 8 factorial over 2 factorial. Is that the same thing as this number? Well, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 2's cancel. 1's cancel, I guess. And we're left with 8 times 7 times 6 times 5 times 4 times 3, which is exactly the answer we got before. So the formula matches in that case. All right, so let's take a look at another example. Suppose you have a class of 20 people. In how many ways can a president, vice president, and secretary, president, vice president, secretary, and treasurer be selected from a group of 20 people? All right, so here we have 20 people, and we need 4 of them to serve, and the order of selection matters. Okay, so since our order matters, and we're selecting from 20 people, 4 of them, the answer is going to be 20p4. All right, and this is 20 factorial over 16 factorial. It's also 20 times 19 times 18 times 17, which is 116,280. Okay, so if the order of selection matters, we're using permutations to count them. And this is going to be our formula when order matters. But it's possible we have a situation where order doesn't matter. Suppose we were selecting not a president, VP, secretary, and treasurer, but maybe just some people to serve in the student council. So we had 4 of them. In that case, it doesn't matter the order that we select them, it just matters who the 4 are. And so we're going to have a slightly different rule for counting those. So the number of ways in which R objects can be chosen from a set of n objects without regard to order without regard to order of selection is called the number of combinations. Okay, so if order matters, we use permutations. If order does not matter, combinations. All right, and what is our notation? It is NCR. And the formula for this is very similar to our permutations formula, but the only difference is we have an extra factor in the denominator. Okay, and so this is the value if we have n objects chosen R with the order not mattering. This is also, you might see this notation. And the way you would say this is n choose R. So we have n objects, we're choosing R of them. We have 20 people, we're choosing 4 of them to be on the student council. Okay, so let's take a look at an example. A pizza company has 6 toppings to choose from. Okay, you want a pizza with 2 toppings. Okay, so we have 6 objects, and we want to select 2 of them, but the order of selection does not matter. Right? If you have a pineapple bacon pizza, that's the same thing as a bacon pineapple pizza. So the order of selection does not matter here. This is a combinations question. All right, so there are 6 objects. We're choosing 2 of them. We're assuming there's no repeat. Okay, you cannot do double anchovies. Single anchovies is at most on a pizza. Okay, so no double. We're not saying we're ruling out the double situation. We're saying we need 2 different toppings. The order does not matter. That's going to be a combinations. So we're looking at 6, choose 2. All right, that's 6 factorial over 6 minus 2, 4 factorial times 2 factorial. Okay, if you have a graphing calculator, there are built-in functions to do these computations. There's also some available online. But these numbers are so small we could actually just compute it. So this is 720 divided by 24 times 2. Okay, and you could type this into a calculator, or you could just believe me that this value is 15. All right, so if this pizza, and this would extend to however many toppings the pizza parlor offers. So maybe there's 20 toppings. We would still use this combinations rule. Okay, so to recap, if the order matters, we're using permutations. If the order does not matter, combinations. Okay? And if we're doing something and then another thing and then another thing, we keep multiplying them together. So if we wanted to pick 2 different 2-topping pizzas, or if we wanted to pick 2 2-topping pizzas, maybe we get the same one twice. It'd be 15 times 15. So that's what that fundamental counting principle said. Remember, we multiply the options. Okay, so I love counting problems. So let me know in the comments if you enjoyed today's lecture. Otherwise, I'll see you in the next one. Bye-bye.